Hey guys, so today I'll be covering the topic of magnetism and electricity. We will use the subsequent sessions to cover electromagnetism. So let me start with talking about magnets. Please give me a minute. Okay, so let's start with magnets. So I'll explain what a magnet is, what a magnetic material is, and what a non-magnetic material is before I dive straight into magnets. So a non-magnetic material a magnetic material have two primary distinctions. The distinction is that a non-magnetic material is not capable of behaving like a magnet or as a magnet under any circumstances, whereas a magnetic material can behave as a magnet under certain criteria or conditions being met. I'll explain what they are. So magnetic material can behave as a magnet, whereas a non-magnetic material under no circumstance can behave as a magnet. So let's understand the existence of magnetism on a much smaller scale. So if I assume the distribution of atoms or the layers of molecules in a magnetic and a non-magnetic material, here for a non-magnetic, a magnetic, and a magnet, we notice a few primary distinctions. A non-magnetic material has the arrangement of molecules in random, and in addition to that, there isn't an existence of something called as a dipole. A dipole is very simple. For you, a grade 10 student, just remember a dipole is the separation of the positive and the negative charged centers in a molecule. That's it. That's all a dipole is. A non-magnetic material does not have molecules present or does not have dipoles existing within the molecules or molecules existing as dipoles. A magnetic material, however, does have its molecules existing as dipoles, although there is one catch here. While they exist as dipoles, if you notice, they are not aligned in a particular direction. This exactly is the reason why a magnetic material initially does not behave as a magnet. And to make it behave as a magnet, all we need to do is we need to arrange the dipoles as such. So all dipoles need to be arranged in a systematic order. And if you are able to achieve that, you simply achieve the effect of converting a magnetic material into a magnet. So whenever the dipoles are arranged, this causes the existence of poles. This is, I would say, a bird's eye view of understanding the difference between a non-magnetic material, a magnetic material, and a magnet. Obviously, magnetic materials and magnets are made up of similar substances because they need to have the existence of dipoles. The difference between a magnetic material and a magnet primarily is the arrangement of the dipoles, which creates the existence of poles. Now, for simplicity, we assume, remember, poles always exist in pairs. So, dipoles. So, a north-seeking pole is called as a north pole or an N pole. A south-seeking pole is called as a south pole. So, for a magnet, based on its behavior, you can name one of the poles as a north pole and the other as a south pole. That's it. Moving further, here is again the rundown of a magnetic and a non-magnetic material. So as discussed here, a magnetic material is one which can be magnetized. The process of converting a magnetic material into a magnet is called magnetization or magnetizing. Now, a magnetic material is, again, let's say it does interact when another magnet is present, simply because another or the presence of another magnet produces something called as a magnetic field around it. And a magnetic material does interact in a magnetic field. Please notice I'm using the word interact and not attract, simply because when I say interact, I could mean either attract or repel. There are different types of magnetic materials. Although this is outside the scope of your syllabus, you can understand that magnetic materials are broadly categorized into three categorizations. That is diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials are a class of magnetic materials which are weakly repelled in a magnetic field, para weakly attracted, ferro strongly attracted. In fact, most of our magnets are ferromagnetic materials which have their magnetic dipoles or magnetic poles, the dipoles arranged in such a way that they appear to be magnetized. So ferromagnetic materials are again further classified as either hard or soft, depending on how well their magnetism is when magnetized. Remember, hard magnetic materials are such as steel and alloys, alcomax, magnetite. So these are difficult to magnetize. But while they are difficult to magnetize, they do not readily lose their magnetism. In other words, once you get them magnetized, it is difficult to make them lose their magnetic properties. So such magnetic materials are called hard magnetic materials. Soft is obviously the inverse of this. Soft magnetic materials are magnetic materials, specifically such as pure iron, also known as soft iron. So these materials can be easily magnetized and easily demagnetized. In fact, most of your electromagnets are made of soft magnetic materials. In fact, even the core of a transformer is made up of a soft magnetic material, owing to this specific property of a soft magnetic material, that is, it can easily be magnetized and demagnetized. Non-magnetic materials, again, these are magnetic material, these are materials, again, could be metals which do not interact in a magnetic field at all. Now, let's understand magnetic fields. So before you understand what a magnetic field is, please remember that magnetic field as a concept or a quantity is an imaginary quantity. Please make sure you understand this. If you show me where if I have a magnet in my hand, I cannot show you where the magnetic field is. I can only help you understand its presence. Although from a quantifiable perspective, magnetic field is an imaginary quantity that we have invented to help understand, interpret the behavior of magnets and magnetic materials. A simple experiment that you've performed in school as well is take a bar magnet with a north and a south pole and sprinkle iron filings around it. You'll notice that the pattern formed is exactly similar to what you see on board. You'll notice imaginary lines popped up which travel from the North Pole to the South Pole. If you place a compass, you'll notice that the compass aligns exactly in the direction in which these lines are being formed. Please notice a few other things as well. You'll notice that closer to the magnet, you will see more number of field lines. And as you go farther away from magnet, you'll notice that the number of field lines I'm drawing in close vicinity will reduce. This is done on purpose because magnetic field strength or the ability of a magnet to let's say make or force other magnets or magnetic materials to interact with it is dependent on distance, or it is inversely proportional to the distance. The closer the materials are, the stronger the interaction of the behavior. The farther the materials, the weaker the behavior. In other words, the lines being so close indicates a stronger magnetic field, a stronger magnetic field, and the lines being so further apart as you go farther away from the magnet indicates a weaker magnetic field or a weak magnetic field strength. Again, please remember these imaginary magnetic field lines are drawn to help understand the behavior of a magnet. More lines are drawn closer to indicate a stronger magnetic field. Lesser lines are drawn as you go farther away from the bar magnet to show a weaker magnetic field. There are a few rules and characteristics you need to remember for magnetic fields for grade 10. Let's start with the first one. The first one is with respect to the direction. The direction of magnetic field lines is always such that outside the magnet, the imaginary magnetic field lines are always drawn from north to south. Outside the magnet, they're always from north to south. You can probably notice this from the direction of the arrow marks drawn. And inside the magnet, very important, inside the magnet, the direction of the magnetic field lines is south to north. I'll explain the reason for this. Inside the magnet, it's from south to north. So if you notice, outside the magnet, it's north to south, and inside the magnet, it's south to north. What this does is, this makes sure that the magnetic field lines always form a closed loop. They always form a closed loop. This is going to be different from electric fields, as you will notice further in the class. So this forms a closed loop. The direction of magnetic field lines being north to south outside the magnet and south to north inside the magnet forms something known as a closed loop. Next, two magnetic field lines do not overlap. This is a question I often get from students. Why are you not supposed to overlap magnetic field lines? You're not supposed to overlap magnetic field lines simply because at any given point, for example, here at this given point, the tangent drawn to this curve gives me the direction of the magnetic field line. So that means here, the magnetic field line is, let's say, downwards. At this point, it would be slightly southeast. At this exact point, it's exactly towards east. This could be northeast. Again, this could be north. In other words, at every single point, a tangent drawn to the imaginary magnetic field line gives me the direction of the magnetic field. So tangent drawn gives me the direction of the field. Again, this begs the question, why can't two magnetic field lines overlap? The simple reason being, if two magnetic field lines overlap, you will have two different possible directions for the magnetic field at the same point, which is practically impossible. So that is exactly why they do not overlap. So please remember, magnetic field lines north to south outside, south to north inside, so that they form a closed loop. Two magnetic field lines do not overlap, and a tangent drawn to the direction of the field will give me direction of field line, will give me the direction of the field at the given point, wherever I've drawn the tangent. Please remember these properties. Again, here's the experiment I spoke of. If you have a bar magnet and if you are going to just sprinkle iron filings, tiny iron filings around it, you will notice the magnetic field pattern exactly as drawn here. Next, we also should realize that Earth itself behaves as a magnet. If you are wondering the reason, the most forward research that I am aware of tells us that the molten core or the movement of the molten core in the Earth's core helps the uh, uh, helps the Earth behave as a magnet. Although again, this is outside the scope of your syllabus, so you need not worry. Just remember that the Earth's magnetic south is here, the magnetic north is here. If you notice, it's the exact opposite as the geographical north and the geographical south. So near the geographical north pole is the magnetic south pole. Near the geographic south pole is the magnetic north pole of the magnet. Again, they do not align exactly with each other. They do have a certain angle between them. Please find out what that angle is called. There's a special name to it. Please figure out if you're interested. Again, because Earth behaves as a magnet, the magnetic field lines go from north to south outside. Inside they go from south to north. Okay. So again, these are the rules of electromagnetism. I will come across or I will go into these rules in the subsequent classes when I'm done with charges entirely. Charges, current, voltage, resistance, combinations of resistors, batteries entirely. Until then, I'll put a pin on this. Now that we're done with magnets, I'll give you guys a quick 10-minute break. So post this, I will be continuing with charges and I'll finish the given topic. Back. Let me start with charges first. Okay. So let me start with what is a charge. So most students get very perplexed when asked about the definition of a charge. Please remember, it's very simple. It's the exact same definition that you have for mass, except that you change one word. So how would you define mass? Let's start with that. So mass is usually, again, this is one of the most common statements you've heard everywhere, including your teachers. Say mass or matter is anything that occupies space. Although that is the right or the apt definition, that is a very simple definition. A slightly more nuanced definition that you can say is mass is that property of a body. It's an intrinsic property due to which the body is able to exert and also experience a gravitational force. Not gravity, gravitational force. Similar to this, electric charge is that property of a body due to which, again, an intrinsic property of a body due to which the body is able to experience and also exert an electrostatic force. That's it. An electrostatic force. Again, I use the word intrinsic because mass and charge are those properties which are not influenced by external factors, such as pressure, temperature, so on and so forth. So mass is that property due to which the body exerts and also experiences gravitational force. So charge is that property due to which the body exerts and experiences both an electrostatic force, not field, force. Now, what are the two classification or categorization of charges? We have negative and positive charges. A simple example of a negative charge is an electron. A simple example of a positive charge is a proton. As simple as that. So here's an example given. So if polythene and perspex can be charged by rubbing them with a dry woolen cloth. When two charged polythene rods are brought close together, as shown, they repel each other. The same thing happens when two perspex rods. However, a charged polythene rod and a charged perspex rod, again, two opposite charges attract each other. So this is the law of attraction and repulsion of charges. The law of attraction and repulsion of charges is very simple. It simply states that like charges repel each other and unlike charges attract each other. What do I mean when I say like charges? A like could be either two positive charges or two negative charges. So when you try to bring two positive charges close to each other, even charged bodies for that matter, not necessarily charges, although they are different. I'll come to that. So when you bring two positive charges close to each other or two negative charges close to each other, they repel each other. What do I mean when they say repel? When I say they repel each other, they basically exert a repulsive force, or they try to move away from each other. Or in other words, the forces acting on them are away from the line joining their centers. What does the law of attraction say? When you bring a like and an unlike, when you bring two unlike charges closer to each other, that is a positive and a negative, then they attract each other, or the force acts along the line joining the two charges or the centers. So again, please remember, like charges repel, unlike charges attract. This is the law of attraction and repulsion between charges. And the closer the charges, the greater the force between them. In other words, the electrostatic force of attraction is inversely proportional to the square of the distance between the charges. That's the implication by this statement. The closer the charges are, the much stronger the force. When I say stronger, I mean any type of force. It could be a force of attraction or a force of repulsion. So students always get confused between a positive and a negative charge and a positive and a negative charged body. So let me make that distinction very clear. An example of a positive charge is a proton, while an example of a negative charge is, as stated, an electron. However, a positively charged body and a negatively charged body are different. A positively charged body is much, much different from a negatively charged body. And they're not the same as a positive and a negative charge. I'll explain how. So a negatively charged body obviously will have a surplus of electrons, making the entire body have basically a surplus of electrons and a deficit of positive charges to counter them, thereby making the body overall negatively charged. A positively charged body, again, remember, does not mean it has more protons and electrons. A positively charged body means there is a deficit of electrons. And calling it a deficit of electrons is not the same as calling it a surplus of protons. Simple reason, whenever bodies exchange charges to become positive or negatively charged from a neutral position, they never exchange protons, they only exchange electrons. Please remember this. So a neutral body will have equal number of positive and negative charges. A positively charged body will have a deficit of electrons. That means it will have lost electrons. It will have lost electrons, whereas a negatively charged body will have recently gained electrons. Very important to understand this distinction. A positively charged body will have lost electrons. A negatively charged body will have gained electrons. Either ways, the quantity that is being lost or gained are the electrons. Why electrons? Why not protons? It always boils down to the structure of an atom. The atom contains a center which is made up of protons and neutrons called the nucleus. Around the nucleus revolve the electrons in fixed orbits. So here are the protons and the neutrons, and here are the electrons. Please remember that for the sake of stability, it is far more easier for the atom to get rid of an electron than a proton or a neutron. And in fact, that is what happens. Under normal conditions, atoms always get rid of electrons, especially electrons in the outermost shell or the outermost orbitals, we learned in chemistry, rather than the innermost, even the innermost electrons, let alone protons. So the medium of transaction between bodies which are getting charged is always electrons. So you lose electrons, you have a deficit of electrons, making you positively charged. You gain electrons, you have a surplus of electrons in that case, making you negatively charged. That's it. Please remember again, the medium of transaction or the charges that are lost or gained are always electrons, never protons. Never. So again, a body is neutral does not mean it has equal number of uh, positive charges and electrons. That just, it doesn't mean that it has no charges. It means that it has equal number of positive charges and negative charges. Negative charges being the electrons, the positive charges being the ions, which are deficit of electrons. For example, if I take ion, Fe2 plus is an ion. So this is an ion that has recently lost 2 electrons. So this is the example of a positive charge present inside a body. The example of a negative charge is a free electron. Please remember, these are the positive and the negative charges that interact, causing the entire bodies to be positive or negative, not protons, never protons. Except for an example of a positive charge, I have and I will never use protons as examples anywhere else, or I'll never use them anywhere else in general. So let's understand what are conductors and insulators. So broad definition, conductors are materials which allow electricity or current or electrons to pass through them more readily or with lesser amount of energy being absorbed. Metals are examples of perfectly good conductors. Insulators, on the other hand, are materials which do not allow electrons to pass through as readily or as freely as conductors do. That doesn't mean that insulators cannot act as conductors. It's just that the prerequisite conditions and the energy required to allow electrons to pass through insulators is far, far, far higher when compared to conductors. It has something to do with a concept known as energy band gap. You are free to research more about this, although this is outside the scope of your syllabus for grade 10. Semiconductors, however, are materials whose conductivity lies in between conductors and insulators. This is another way of saying that their conductivity depends on temperature. The conductivity of semiconductors is proportional or is related. Let me not use the word proportional. It is related to the temperature. So higher the temperature, better the conductor, lower the temperature, poorer the conductor, the semiconductor, let's say. So conductors are materials which readily have a sea of or a surplus of free electrons, and they readily are able to conduct them when provided a potential difference between their terminals. We'll come to what potential difference is in a while. Insulators do not readily allow. Again, like I said, being an insulator doesn't mean that you never allow charges. It's just that the energy required to allow charges to flow through them is very high. So usually in insulators, charges are always accumulated only on the surface, and this is mostly achieved by rubbing. And because electrons cannot traverse through the body, they are usually present statically on the surface of an insulator. One simple example of charge accumulation through rubbing is the example explored here. When you rub a polythene rod and a silk cloth, you will notice that in the triboelectric series, the polythene rod is obviously far, 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 I think, higher than the silk cloth, making sure that the polythene rods, which become positively charged, again, lose electrons from the surface. The silk cloth, however, becomes negatively charged and they have electrons existing or persisting on the accumulating on the surface. So conductors CO free electrons, easily able to allow the electrons to pass from one into the other by applying a potential difference. Insulators, the exact opposite. Semiconductors, the conductivity lies between that of a conductor and insulator. It keeps varying based on the temperature. Now, moving on, let's understand what earthing is. The process of earthing is simply the process of transferring excess charges from a given charged body to the earth. And remember, earth is capable of absorbing any type of charge, positive or negative. In other words, what I'm trying to tell you is, if you have a positively charged body, which has a surplus of positive charges, again, not protons, ions. And if you connect this to the ground, as shown, and this is the electric symbol for grounding or earthing, the electrons will flow from the earth to the charged body. The electrons will flow from the earth to the charged body, thereby neutralizing these positive charges and making sure the body is eventually neutral. Same way, if you connect a negatively charged body to the earth or to the ground, or you earth it, then electrons will travel from the charged body to the ground, thereby neutralizing the charges. Again, please make sure to notice, I'm only talking about the motion or the movement of electrons because it is the movement of electrons that causes charge movement or current, to be specific. Now, there are different ways to induce charges. One of the most simpler ways to induce charges is through the process of induction. So let's understand what induction is through this depicted example. So let's say you have a positively charged rod that is brought in close vicinity to a neutral metal sphere. Again, I'm using metal because metals have charges. I'm saying neutral because there's equal number of positive and negative. And when you bring a charged rod in close to it, there is a charge separation that occurs within the metal sphere. You'll notice that within the metal sphere, the negative charges appear or accumulate on that surface, which is far closer to the rod. And due to electrostatic attraction, they appear or they accumulate on the face, which is much closer to the rod. Again, due to electrostatic repulsion, the positive charges accumulate on that face or that end of the rod, which is as far on the sphere, which is as far away from the rod as possible. So this is known as charge separation. Now, so after this, again, if you carry out the process known as earthing, whether you do it by finger or you connect a wire directly to the earth, doesn't matter. So you conduct the process known as earthing. That is, you connect this part of the metal sphere to the ground. Please remember, electrons will flow from the earth to the body, neutralizing these positive charges, which are as far away from the charge as possible. And when it neutralizes, this causes the metal sphere now to become overall negatively charged. Negatively charged. The reason it becomes negatively charged overall is because these negative charges are held in position and they are not lost to earthing due to the fact that there is another positively charged rod close to it. Due to electrostatic attraction, they are held in place, while the grounding removes the positive charges by accumulating excess of electrons from the earth to the sphere, thereby neutralizing them. And this causes the entire sphere to become negatively charged. And now we can remove the rod and the negatively charged and the negative charges will just localize throughout the metal sphere, making it making the uncharged metal sphere in the initial state to be a charged or negatively charged metal sphere. This is how the process of induction works. Next, let's understand what charges are. In fact, there's a simple experiment that is performed to detect the presence of charges. This is called the gold leaf electroscope experiment. I will explain the premise in very simple terms. Remember again, through the process of induction, I will bring a charged rod a positively charged rod in close vicinity to this metal cap, obviously charge separation happens. The negative charges, the electrons accumulate on that face or on the metal cap because that is closest to the positively charged rod. And the positive charges, which are the ions, not protons, accumulate on the farther end. And when the positive charges accumulate on the farther end, you'll notice that positive and positive repel each other, which causes the gold leaf to raise by a certain angle due to electrostatic repulsion. So the raising of the gold leaf due to the electrostatic repulsion between the accumulated positive charges on the farther end proves the presence of charges, which is the whole premise of the gold leaf electroscope. Again, please remember, the metal cap is held in place by an insulator and is placed in a glass jar, preferably in vacuum, to make sure that there is no other charge interaction. Now coming to the quantity of charge, current, voltage, let's understand what they are. I'll discuss all three quantities and then I'll go into the details one by one. So charge, again, as we've discussed, is a physical quantity denoted by the symbol either capital Q or small q, doesn't matter. The unit of charge is Coulomb, C-O-U-L-O-M-B, derived unit, again, not a fundamental unit, denoted by C. One of the simple formulas or the simplest formulas for charge is Q is equal to N into E, where N is the number of charged particles. E is the value of charge on each electron, which is a constant. The value is, sorry, let me write E, not epsilon. The value of E is 1.6 into 10 to the power of minus 19 Coulomb. The charge on an electron is negative E, whereas the charge on a proton is positive E. Please remember this. The charge on an electron is negative E. The charge on a proton is positive E. E is a constant whose value is 1.6 into 10 power minus 19 Coulomb. As far as you are concerned, this is the smallest amount of charge that exists in nature. Although, yes, in grade 11, grade 12, when you learn about further set of or family of particles known as elementary particles, you'll understand that even this charge can be broken down. So charge, unit Coulomb, formula Q is equal to N. I'll explain current and voltage as we come across those concepts in the further parts of this revision. Now, let's understand what electric fields are. We just discussed what magnetic fields are and what are the rules that we associate with them. There are, again, very similar rules for electric fields. Let me make you understand them one by one. So what are electric fields or electric field lines? So again, similar to magnetic field lines, electric field lines are imaginary lines that we draw in the vicinity of charged particles to help understand, interpret charge behavior. That's it. So when you assume a point negative charge, you will assume electric field lines coming towards the negative charge. Please remember, a point negative charge will have all the electric field lines coming towards it. Similarly, a point positive charge will have all the field lines going away from the given charge. As simple as that. By logic, when you're showing electrostatic attraction between a positive charge and a negative charge, you will show electric field lines going out of a positive charge and going towards a negative charge. As simple as that. So we will show electric field lines going out of a positive charge towards a negative charge. So this depiction here is electrostatic attraction. I can also show repulsion. Let me draw it here. Electrostatic repulsion looks something like this. Between a positive and a positive, the field lines refuse to interact with each other. Again, why do they refuse to interact? Because this is electrostatic repulsion. Because they're positive, I'm drawing the field lines away. If they were too negative, then I would draw the field lines inwards, but still showing repulsion exactly in the same pattern, except for the arrow mark change. Whenever you have Plates, however, plates filled with positive and negative charges, you'll notice that the field lines throughout the uniform cross-sectional area of these plates are also uniformly distributed. If you have more field lines, please remember this just indicates a stronger field. If you have less number of field lines, that indicates a weaker field. Obviously, closer to the charges, you have more field lines being drawn. As you go farther away, you have less field lines being drawn, owing to the fact that here there is a weaker electric field, and closer to the charges, there is a stronger electric field. An electric field, again, also impacts the behavior of other test charges in the vicinity of a source charge, which is producing the field. We will discuss their behaviors in a short while when I discuss voltage. So this is how you draw the electric field pattern. Similar to magnetic field lines, they have similar rules. Two electric field lines do not overlap. A tangent drawn to the electric field line, imaginary electric field line drawn, gives you the direction of the electric field at that point. And electric field lines always go from positive to negative. One important distinction for electric field lines, which magnetic field lines do not have, is electric field lines do not form closed loops. Another smaller difference is the fact that a magnet will always have a north and a south pole, whereas and the magnetic field lines are drawn as such. Whereas in electric fields, you can have an isolated negative charge. You can also have an isolated positive charge. It is not necessary that a positive and a negative always have to exist within close vicinities of each other. Again, here you have a strong electric field line, a weak electric field line. You understand the strong electric field line because the field lines are much closer here. Weak electric field lines here because they are much farther away from each other. Now, let's understand what current is in a simple circuit. We all know, we've used the word current in a lot of contexts before. Now let's understand its significance. So what is current? Mathematically, current, in fact, one of the 7 fundamental quantities denoted by I, and the unit ampere denoted by A, is just the amount of charge passing through a given point in a wire. So mathematically speaking, when you say speed is the rate of change of distance, you do distance by time. When you say velocity is rate of change of displacement, you do displacement by time. When you say acceleration is rate of change of velocity, you say velocity by time. So because current is defined as the rate of flow of charges, because you use the word rate of, you define current as the charge flowing per unit time. This is its formula. So you can also derive the unit. Ampere is nothing but coulomb per second. Or coulomb, which is a derived quantity, is just ampere into second. That's it. So current, remember, this is a concept the students always misconstrue. Current is a scalar, not a vector. The reason current is a scalar and not a vector is because current is a measure of amount of charge flowing through a given point in a given time interval. That's all it is. But yes, I know that we associate direction to current, but in reality, we are associating direction to the conventional flow of current, which is opposite to the flow of charges. So if you have a battery connected to a bulb in a circuit as shown, you'll notice that this is the positive terminal of a battery. This is the negative terminal of a battery. The conventional flow of current is assumed to be from the positive terminal to the negative terminal. So this is the direction of conventional flow of current, which is from positive to negative, but the direction of flow of charges is always from negative to positive. Why negative to positive? Simply because charges flow from a region of higher concentration, which is the negative plate, to a region of lower concentration, which is the positive plate of the given bat. That's it. So current, by definition, amount of charge flowing per unit time, hence scalar. The conventional flow of current in a circuit is assumed always positive to negative, which is opposite to the flow of charges, which is from negative to positive. Please remember this. Again, current is charge by time, or charge is current into time. So what is potential difference? Let's understand what potential difference is in very simple terms. So in fact, it's also called not just potential difference. There are 4 different names to it. I'll write each name and I'll explain what is associated, or the formula associated, or the concept associated with each part. So there are 4 different names you call this concept. You call this as voltage. You call this as potential. You call this as potential difference. You also call this as EMF. EMF stands for electromotive force. You will soon learn about this. So what is potential? Let's have a standard definition. Simple. Potential is defined as the work done per unit charge. The work done per unit charge to move a given charge from point A to point B against an external electric field. That's all it is. What is potential? It is the work done per unit charge to move the given charge from one point to another against an external field. If you notice, this is a very similar to the definition of potential in a gravitational perspective, as you will learn in higher classes. So formula, potential V is equal to work done by charge, or the energy consumed, I'll denote by U, divided by charge. When you look for potential in a circuit, the potential across 2 points in a circuit, then you call it voltage. By Ohm's law, you know that voltage in a circuit is proportional to the current, giving you the formula. V is equal to I into the constant of proportionality here is the resistance R. So when you call it voltage, it has a formula V equal to IR. When you call it potential, it has the formula V is equal to W by Q or U by Q. When you call it potential difference, then it is just the difference in the potential between a final point and an initial point. What do I mean by that? Look at this. Let's say you have a charge Q at some initial point, okay, at some point A. Let's say the potential at this point is VA. And let's say at this point, you are trying to move a charge from here to here against some external field produced by some charge. You don't know. Let's not worry about that. So let's say this is point B where the potential is VB. So the potential difference between these 2 points is nothing but the potential difference at the final point, which is B, minus potential at the initial point, which is A. And you can equate this to the potential formula, which is work done per unit charge Q. So if you do W amount of work to move charge Q from point A to B, your potential difference VB minus VA will be equal to the potential, that is W by Q. So potential difference is, in general, potential at the final point to where the charge is moved minus potential at the initial point from where the charge is moved. You can always equate this to W by Q because they are interoperable. What is EMF? Again, outside the scope of your syllabus, remember that EMF, there are 2 definitions. For class 10, you have said that EMF is the potential difference that exists between the terminals of a battery. Another way of explaining it is also the current, that is the potential that is generated within a wire when it is subjected to a changing magnetic field. So for you, just remember the EMF denoted by epsilon. It is a voltage that is generated in a wire when it is subjected to a changing magnetic field. A changing magnetic field. So the stronger the faster the rate at which the magnetic field changes, the greater the value of EMF that is produced, or the potential difference that is produced between the ends of a wire. Another definition of EMF, like I said, is also the potential difference across the terminals of a given battery. So this is EMF, this is potential difference. So there are 4 different names we call voltage by. It does not matter what name we use. The concept, however, is the same. Again, because the concept is the same, these definitions are interoperable or interchangeable. Please understand all of these. The unit of potential is, or voltage is volt. This is one of those quantities where the symbol for the quantity is V. The symbol for its unit, which is volt, is also V. The symbol for its unit is also V. Please do not get confused. This is one of the few, in fact, only physical quantities which has the same same symbol for the quantity as well as its unit. Do not get confused. Again, potential difference in a circuit. So the total potential difference between the terminals of the battery, let's say, are 3 volt. Then the potential difference between the two components in the circuit should and must add up to 3 volt. In other words, the potential across the battery should be equal to the potential or the voltage drop or the potential difference across all the components in the circuit, all the serial components in the circuit combined. We'll use this more when we come across resistance and series and parallel combinations of resistors. Next, we will go up again. I'll give you a brief bird's eye view of what I'm about to cover next. I'm about to cover resistance. I'm about to cover types of resistors. I'm about to cover Ohm's law. I'm about to cover series parallel combination of resistors and how you solve series and parallel circuits. And then I'll explain about power and the mains circuit and safety precautions to be taken. But before that, I'll give you guys a small 5-minute break. Please take this break. Hey guys, let's continue. So I'll continue with the other parts. Specifically post resistance. Okay, so let's understand what resistance is in very simple words. So resistance is the opposition faced by a wire is opposition faced by a charge as it passes through a wire or any other electrical component. Please remember, resistance does not exist at a particular point. It exists throughout the wire or even through the component that you have placed. It is just that we denote resistance at a particular point in an electrical circuit. Ohm's law states that voltage V is proportional to I. Convert a proportionality into an equality. You multiply a constant I times K. That constant K is nothing but the resistance of a wire, which remains a constant for a given value of voltage and corresponding value of current. So V is equal to IR, or in other words, R equals V by I. The unit of resistance is Ohm, giving you Ohm as equal to volt by ampere or volt per unit ampere. So here are a few factors that affect resistance. In fact, we'll write a new formula from this. So the factors affecting resistance are the length of the wire. Basically, resistance is directly proportional to the length of the wire. Cross-sectional area, in fact, it's inversely proportional. Also, R is inversely proportional to the area. It is proportional to the material of the wire or the resistivity, which we'll understand. It is also proportional to temperature, although we do not explore this concept. Just remember this, R proportional to L, R proportional to 1 by A. You can combine these two and you can write R proportional to L by A. Same logic as before. How do you convert a proportionality into an equality? You multiply a constant. Constant K into L by A. The constant K here is known as resistivity rho. Resistivity for a given material is defined as the resistance per unit length per unit cross-sectional area for that given material. Please remember, resistance is a constant only as long as what length and area are maintained constants. Voltage and current can change, does not matter. Voltage, current can change however they want. Resistance will still be a constant as long as length and area are changed. Same, sir. But when length and area are changed, even resistance, which is assumed as a constant in Ohm's law, will also start to change. But what will not change is the resistivity of the material. resistivity will remain constant as long as the material is the same. In other words, let me give an example. If I take two copper wires, one thin and then one thick, both of them will have the same resistivity because they're both made out of copper, and resistivity is defined per unit length per unit cross-sectional area for the same material. The resistances, however, can be different. The thicker copper wire will have a greater cross-sectional area and thus lesser resistance. The thinner wire of same length will have probably less cross-sectional area and more, or definitely have less cross-sectional area and more resistance. Temperature, remember this general rule. For conductors, resistance will increase with temperature. For semiconductors, it will decrease with temperature. It is the same for insulators too, although the gradient is much, much lesser. Next, resistance components. Again, we use scientific prefixes explored in unit 1 here. 1 kilo ohm is 1000 ohm. A mega ohm is a 1 into 10 to the power of 6 ohm. Again, whenever we discuss resistances in circuits, we usually make it a point to keep all these factors constant. Although sometimes, yes, length and cross-sectional area are also varied because you have the other formula, R equals rho L by A. Here are the different type of resistors you come across. One is a variable resistor or a rheostat. A variable resistor or a rheostat is just a device whose resistance can be varied by adjusting a knob along the length of the entire rheostat. Basically, you turn a knob along the length of the rheostat, which is just wires encompassed like this. And as you turn, you make sure that current passes through a longer length of the wire, thereby increasing resistance. So sliding it to the right increases the resistance, to the left decreases the resistance. What is a thermistor? As the name suggests, it's an amalgamation of two words, thermal resistor. It's a resistor whose resistance will depend on the temperature. It will have a high resistance at a lower temperature, and it will have lower resistance at higher temperatures. If I go back to the previous page here, we discussed that resistance increases with temperature for a conductor, and for a semiconductor it decreases. And since thermistors have that inverse relationship where an increase in temperature will decrease the resistance, we know that they contain semiconductor or semiconductor materials. LDR stands for light dependent resistors, which, as the name suggests, are resistors whose resistance or value of resistance will depend on the light that is incident on it. So greater the intensity of light, lower the resistance. Or in other words, it will have a high resistance in a dark space or a darker area, and low resistance in a lighter area owing to the higher intensity of light that is incident on it. A diode is a semiconductor material. You don't have to understand how it works. Just remember, a diode is basically like a one-way street. It's a conversion of a two-way street into a one-way street. It only allows current to flow in one possible directions, not both the directions. If you want me to show here, this is a circuit symbol of a diode. A diode has a positive and a negative. It allows current to flow like this, positive to negative, but it allows current to flow like this, but it does not allow current to flow like this. That is negative to positive. It only allows current to flow in one possible direction. That's a diode. An LED is also a type of a diode which produces light as current passes through it. That's it. Remember, diode, an LED, thermistors, variable resistors. Variable resistors maybe not so much, but thermistors, LDRs, diodes, and LEDs are non-ohmic devices, which means they do not have a linear relationship between voltage and current in their behavioral pattern. Only devices which have a linear relationship between voltage and current are ohmic devices, or devices which obey Ohm's law. R equals V by I or V equals IR. These devices do not obey Ohm's law. In fact, if you want me to show the pattern of current versus voltage behavior for a diode, this is exactly how it looks. The current versus voltage behavior is like this. This is a point known as a knee voltage. Please remember that. or this is the point where the diode starts to conduct. Think of it that way as well. So here are the devices shown in picture and their corresponding circuit symbols. Yes, it is important that you know the circuit symbols. And all these devices do not have a polarity except for a diode. A diode's polarity is this. This is the positive, this is the negative part. None of the other devices have a polarity inherent, but they do develop polarity because they will develop potential difference across them as current passes through each one of them. Again, as Ohm's law says, the current is proportional to potential difference. Again, so if you notice here, a tungsten filament, a semiconductor diode are both examples of non-ohmic devices. Simple reason why they're non-ohmic devices because they have a non-linear relationship between current and voltage. Next, let's look at series and parallel circuits. So what we'll do is I'll take an example of a series circuit, a parallel circuit, show you the derivation of resistance in series and parallel. Let's assume that we have a battery here or of voltage or of terminal potential difference, V. Let's say I have two bulbs in series. For good measure, I'll also connect voltmeters to measure the voltages across each one of them. Let's say the voltmeter across the first bulb is V1 and the second bulb is V2. Let's assume that current flowing in this direction is I. The current flowing to the first bulb will be I. The current flowing to the second bulb will also be I. I'll give a very simple logical explanation for this. Current has only one possible, or charge has only one possible path to go, which means the value of current or the amount of current flowing and the amount of charge will be the same. Don't assume that current will be high here. As soon as it enters here, it will become low. No, that's not how it works. I've told you this before. The lamp or a resistor is an indication or is a depiction of resistance. That doesn't mean that there is the resistance here is zero and resistance here is some non-zero value. The resistance is uniformly distributed throughout the wire, which means the current value here will be the same as the current value here. They are not different. The current value here and the current value here are the exact same values, which is also the same as current value here as well, which is also the same as current value here as well. Please remember that. Current value will be the same throughout the wire because resistance is uniformly distributed, not present only where the bulbs are present. This is just for depiction purposes. So if you assume the bulb 1 with resistance R1, bulb 2 with resistance R2, you can write that in series, voltage will add, current will stay the same. So series, voltage is added and current I will stay the same in series, which means total voltage V is equal to V1 plus V2. Total voltage, Ohm's law can be written in three ways. V is equal to IR, I is equal to V by R, or R is equal to V by I. So I'll use this first depiction here. V is equal to IR. V is equal to I into, let's say, equivalent resistance R series. V1 is I into R1 plus V2 is I into R2. Cancel I everywhere. You get R series equals R1 plus R2. So in series, resistances are added. In other words, the overall resistance is greater than the individual resistance. Moving on to the parallel part. For a parallel circuit, again, let me place 1 voltmeter here and 1 voltmeter here. Although remember, this is the exact same connection. This connection leads to here. This connection also leads to here. This connection leads to here. This connection also leads to here. In other words, even though I'm placing two different voltmeters, I'm measuring the voltage across the same point, which means both the voltmeters, V1 and V2, will give me the same reading. So in parallel, voltage V will remain the same across two parallel elements. Current, however, look at it this way. Current is I here. As soon as current enters this junction, current I, it has two possible paths to go. One part of the current will go through here, I1. One part of it will go through here, I2. So in parallel, voltage remains the same and current is split or added. Split and added. So total current I can be I1 plus I2. If you assume this bulb having resistance R1, this one R2, and the equivalent resistance R parallel, I'll use Ohm's law equation I is equal to V by R. I is equal to total voltage V divided by total resistance R parallel, let's say. I1 is V1 by R1, I2 is V2 by R2. Here, remember the total voltage V is the same voltage across these 2 points, which is also the same voltage as across V1, V2. So V is equal to V1, which is equal to V2. Again, this is because there is no other resistor here. There is no resistor R3 placed here, correct? Please remember that. So V is equal to V1 plus V2. Cancelling V everywhere, you get 1 by R parallel equals 1 by R1 plus 1 by R. As simple as that. That's it. Next, basic circuit rules. Remember, voltage added in series, voltage remains same in parallel, but current gets added in parallel. Please look at these examples. You can pause, take a minute to look at them. When you have cell arrangements as shown, remember cascading of cells from positive to negative, positive to negative, positive to negative will add the voltages. So the individual voltages V1, V2, V3, total voltage is V1 plus V2 plus V3. If you connect them in reverse order as shown, this will be added, this will be subtracted, this will be added, giving you the total voltages V1 minus V2 plus V3. Parallel, however, nothing happens. Parallel, don't worry about the voltages being different. They will be same because if they become different, the calculation becomes more complex, which is outside the scope for your syllabus for grade 10. I'm not telling it's impossible. There is a formula to calculate voltages in parallel, but assuming the voltages are different, but there's a complex formula which is outside your scope. In parallel, remember, voltage remains the same. It's not the R parallel formula. It remains the same. Assuming all the voltages, in fact, are also same. Again, here's the formula that I derived. R series is R1 plus R2 plus R3 plus R4. R parallel is 1 by R parallel or 1 by R effective equals 1 by R1 plus 1 by R2 plus 1 by R3, so on and so forth. This should have been R2, not R. Here are examples, again, discussing the same concept. The last concept that you have is electrical power. Electrical power, in mechanics, we've discovered different formulas for power. Power equals work done by time. Power is also equal to energy or U by time. Power is also I've discussed force into velocity, assuming force is uniform. I know potential V is work done per unit charge, which means work done W can be potential into charge, which means power can be written as potential into charge by time. I know charge by time is current, giving me the formula of VI. I can also rewrite it as I square R, Ohm's law, or I can also write it as V square divided by R. Again, if power consumed is VI, I square R, V square by R, energy will just be all these multiplied by time. That's it. The three ways of representing power are VI, I square R, V square by R. Again, if you have multiple components in a circuit, remember the total power is the sum of individual powers. It does not matter whether the components are series or parallel. Total power is always sum of the individual power of the components which are placed in series or in parallel. Going to the mains electricity, there are a few concepts or names you need to remember. A mains electricity, the 3-pin socket that you've seen in your house, for example, consists of 3 wires, a live, a neutral, and a grounding wire. Sorry, a live wire, and then a neutral wire, correct, and then a grounding wire. Energy is always consumed by your appliance between the live and the neutral. Whereas excess current or the dangerous value of current, which can sometimes be received by mistake or can happen, will be discharged or dissipated through the grounding wire. Switch is a part of a circuit. It is used to turn on or turn off the flow of current in a circuit. A fuse, we know this. A fuse is a simple device which is made up of an alloy. The purpose of a fuse is to break open the circuit or is to switch off the circuit basically whenever current exceeds a prescribed rated value. For example, if a fuse is rated at 13 amperes, as long as current does not exceed 13 amperes, the fuse will act as a closed circuit or as a closed switch or as a switch in an on state, allowing current to pass through. As soon as current equals or exceeds 13 ampere, the fuse, which is made up of two alloys, will bend at different angles because two different metals expand at different rates. And they are designed in such a way that at 13 amperes, the amount of heat generated will bend them at different values like this, thereby breaking open a circuit. A circuit breaker is a fuse which can be used again and again. That's it. That's all a circuit breaker is. A circuit breaker is a device which can be fused again and again. Fuse can be used only once because once a fuse blows or is blown, you cannot use it again. Earthing wire or the grounding wire, again, it's a safety wire through which all the excess amount of charges or the metal parts of an appliance are connected to. This is to make sure that a person touching the metal part of an appliance does not receive an electric shock, even though the appliance is conducting current through itself. Double insulation, again, this is a precautionary measure which is being taken specifically between the live, neutral, and the earthing wires to make sure they do not touch each other by mistake, whether it is during the connection wires that are made during domestic or industrial application, or whether it is during the connection at the socket pin. Here are a few safety precautions you need to take while handling electrical appliances. Please make sure to be aware and in fact, stay away from old frayed wiring. Broken strands means the wire will have a higher resistance at one point. When current flows through, the heating effect may cause maybe enough to melt the insulation, cause a wire. Long extension leads, again, they tend to overheat. Why do they tend to overheat? Because resistance is proportional to length. Simple as that. Wire and socket, wire is water and socket, sorry. Water is a conductor. Not pure water, but water mixed with impurities. Accidentally cutting cables, again, this could also cause electrocution. Electrical energy calculations, remember, energy is measured primarily in two units. Its SI unit is joule, which is from the formula energy is equal to power into time. Again, power can be written in three ways. So I can write VI into T, I square R into T. I can also write V square over R into T. Energy is in its SI unit, that is joule or joule. If you want to convert joule into, let's say, another unit, that is kilowatt hour, all you have to do is to convert joule into kilowatt hour, you have to multiply by or divide, sorry, by 3.6 into 10 to the power 6. To convert kilowatt hour into joule, multiply by the same value, 3.6 into 10 to the power 6. That's it. Kilowatt hour is one of the recognized units of energy, although its SI unit is still joule or joule. Again, 1 kilowatt hour is 3,600 joules. So if you want to convert kilowatt hour into joules, multiply by this, joules into kilowatt hour, divide by this. That's it. So this concludes the first half where I discuss just magnetic fields, magnets, magnetic materials, charge, current, voltage, resistance, and combinations of resistors in series and parallel. So in our subsequent class, which is happening, I think, on Monday, I'll be covering important aspects. That is, I will be covering the series parallel combination, that is combined series and parallel combination of resistors, how to solve them. I will be explaining the rules of electromagnetism, right hand thumb rule, Fleming's left hand rule, that means right-hand rule, the charge rule, and all the other concepts that come as, I think, the working of motor, the working of generator, the working of other components such as loudspeaker, and also the working of a transformer. So we're covering all these other and other additional concepts that I'm forgetting right now, which are a part of electromagnetism. So in the next crash course session, I'll be covering that topic. Post that, we will be moving on to atomic nuclear physics for the subsequent session. And the last session will be on space physics. Thank you for your time, guys. Good luck for your exams.